Hey there, and welcome to the first video that we're going to be looking at in our Unit 3 material, where we're going to actually be applying how we use derivatives with some contextual problems, where we can actually, where does this stuff apply to previous mathematics, or where does it apply in the quote-unquote real world. So this first lesson is going to be looking at related rates. Related rates is something that people kind of have an intuitive knowledge of. If you're driving and you're trying to see, do I have enough time to get over enough lanes to make my exit, or do I have enough time to maybe finish cooking this steak while the mashed potatoes boil, things like that. It's if you're looking at, comparing two different things over the same interval of time, that essentially is a related rate, okay? Think about, you walking in the hallway at school and thinking, okay, well, do I have enough time, compared to how I'm walking to how this person in front of me is walking, do I want to get over now to try and make it to my class, or am I going to beat them? Think about, two people going for a ball on like a soccer field. You can kind of see how fast one person is running versus how fast another person is running to kind of see who's going to get to the ball first. Again, those are just some practical, ways that we could look at applying related rates to something. So this is where our derivatives are going to come into play. So the first few examples here aren't going to be super strenuous. They're really just asking you, can you take a verbal statement and translate it into a math statement? And that really isn't going to be too difficult for us, I think. Looking at the examples here, the first one, the volume of a cylinder is increasing at a rate of 6 cubic feet per second. So here, the word increasing, that is one of our first keywords. That means that we're going to have some kind of a positive value for our rate. And the value that they're giving you is 6, and the rate that they're talking about is changing 6 cubic feet per second. So here, the volume, which I would express as a derivative to be dV dt, the derivative of the volume with respect to time, would be a positive 6 cubic feet for every second. And that's how I would translate the statement that was given to me in English into a math statement with a derivative. So let's take a look at the second problem. The depth of the water of a rectangular pool is decreasing. So there's a keyword right there. And because we're decreasing, that means we should have a negative value of some kind. And they tell you straight out that the rate is 2 inches per hour. So what am I talking about? In this case, we're talking about the depth of the water. So depth of the water, usually we think of that as a height. So I'm going to say the derivative of the height of the pool of water with respect to time is going to be a negative 2 inches per hour. And if you want, you can kind of write it like 2 inches per hour like that. Either way is perfectly fine. So there's your first couple of examples, and I would encourage you to pause the video and try working out these two, see if you can write the expression for these two, and then hit play when you're done. But I'm going to go ahead and start taking a look at them. At rush hour, the number of vehicles at a toll booth is increasing, so that tells us that we're going to have a positive value. And they're giving us the rate of 85 vehicles per hour. So the way that I would express this as a derivative, we're talking about the number of vehicles. So I'm going to say dv, and I'm going to use a lowercase v to, because a lot of times we might use a capital V for volume. I'm going to use a lowercase v for vehicles. The derivative of the number of vehicles with respect to time is going to be equal to a positive 85 vehicles per hour. And so the next one, air is escaping. So we're escaping, so that means our rate is going to be decreasing, so we're going to have a negative value from a spherical balloon. And so air here, if we're talking about the number of air or the amount of air in a balloon, this is going to be volume of some kind. Okay, at a rate of 15 cubic centimeters per second. So here I would say dV with a capital V to represent volume. That's not like a standard in it or anything. That's just kind of what I do to differentiate between volume and anything else that uses a V as a, its first letter, its initial. So the change in volume, the derivative of volume with respect to time, in this case will be a negative 15 cubic centimeters, so centimeters cubed per second. And that is all it really takes to translate a math statement or a given statement in language, in this case English, into a math statement in derivatives. So moving on, now we're going to be taking some familiar things that you've seen, particularly in geometry, and seeing can you write the equations that are given to you in terms of a derivative, so that way you could solve a related rate based off of that topic. So let's take a look at our first example here. Okay, area of a rectangle is equal to length times width. So we're trying to take the derivative of something. And here in the equation, because I have a product of length times width, then that means we have to use the product rule for our derivatives. So the derivative, we're going to take the derivative of both sides of the equation. So on the left side, we're going to just say the derivative of the area with respect to time, so dA dt. And for the length and the width, we have to use the product rule that we saw back in Unit 2, I believe, Section 5, where the notes, or maybe Section 6, is where you saw the product rule. So I'm going to take the first bit, the length, and I'll use a capital L to represent the length, and I'm going to multiply it by the derivative of the second part, which in this case is width. So I say dW dt. So those are multiplied together, and then I take the sum of the next part. So the next part is the second piece of the product that was given to you, in this case the width, and that gets multiplied by the derivative of the first term, which would be the length. So here I'll say dL dt, and there is your equation as a derivative that we would use to solve a related rate for the area of a rectangle. Moving on to the next one, we're going to look at the circumference of a circle. Now the 2 and the 2 pi, this is just considered a constant. So the 2 pi, that's just a number. That's what we would think of as a constant in the equation. And the only variables that we have are the c for circumference and r for the radius. So those are the things that we will actually be doing the derivatives of. So the derivative of the left side, the derivative of the circumference, would be the derivative of the circumference with respect to time, so dc dt is equal to, now the derivative of r, that would just, show that, using the power rule of the derivative, well, we would just take the exponent, we would multiply it and do what the normal power rule says. But we have to show that we're taking the derivative of that, term. So here, this is going to be 2 pi, the constant, times the derivative of the radius, dr dt. There we go, dt. So there's the equation that we would have for the derivative of a circumference of a circle with respect to time to solve a related rate with that formula. Okay, so the rest of these are just kind of practice, okay? Feel free to try and work them, pause the video and work ahead. I'm not going to give quite as much explanation on the rest of these because it's really just a lot of practice, okay? And if there's anything that you're not sure about, send me a message. Let me know when we meet in class, things that you're not entirely sure about. Oh, and I forgot to change the page here. So go ahead and pause the video and try to work out as many of these as you can, and then go back and see what the explanations are. So the volume of a cube here, I'm going to say dv dt for the derivative of the left side. And here I'm going to say 3s squared times the derivative of s, so ds dt. Okay, and so that would be the expression for the volume of a cube's derivative. The lateral surface area, here I'm going to say ds dt, and I probably should have made that more of a capital looking S, but we're going to look at the 2 pi. Again, I'm going to look at this as a constant, okay, so that's just going to be 2 pi in the problem. And the other two pieces, kind of like what we saw on the first example, we're going to use the product rule here. The product rule for our derivatives. So in this case, I'll say r times dh dt plus h times dr dt. And so that is what I would have for the derivative here. The next one, 9, area of a circle. Again, the pi is going to just be a constant, so we'll just treat it like a normal value in the problem, and we understand that when we take the derivative that it's going to get multiplied to whatever that exponent value is. But here I'm going to have dA dt, the derivative of the area with respect to time on the left side, and on the right side, when we go through the power rule for the for the derivative with radius, that would give me 2 times pi, and then we're taking the derivative of the radius with respect to time. The next one, the perimeter of the square. This one is almost so easy that it's going to be confusing for some people. On the left side, the derivative of the perimeter with respect to time gives you dp dt. Now here, the derivative, we would just take the exponent of 1 and multiply it to the 4, so that's just going to be 4. And we're showing, so we have to show that we're taking the derivative of the side with respect to time. So that's all I would have for the derivative equation for perimeter of a square if I needed to use that to solve a related rate problem. Here, next to volume of a cylinder and a volume of a cone. So volume of a cylinder, I hope by now the left side is going to be pretty simple as far as how you're taking the derivative. We're taking the derivative of the volume with respect to time. So here, again, the pi is going to be considered a constant, so I'm not even going to worry about that right now. And the radius squared and the height, I'm going to use the product rule on. So I'm going to take the radius squared and I'm going to multiply it by the derivative of the height, so dh dt. And then I'm going to take the height and multiply it to the derivative of the radius, which would be times 2r times dr dt. And we'll clean that up a little bit. So I'll say dv dt would be equal to pi times all of this, r squared times dh dt plus 2hr dr dt. And moving on to the next one here, again, I'm going to look at the 1/3 pi as just a constant, so I'm not going to worry about that when I do the derivative. So on the left side, the derivative of the volume with respect to time, dv dt, will be equal to 1/3 pi, and we will treat the interior, or we'll treat the r squared and the h with the product rule, just like I did on the last example on 11. So here, basically, we're going to have the exact same thing where we have r squared times dh dt plus 2hr times dr dt. And the last two here, again, I'm going to treat the 4/3 in the volume of a sphere, just like I have in the other problems. I'm going to, just leave the constant out of the derivatives right now. So dv dt, in this case, will give me 4/3 pi, but then I have to take the derivative of r cubed. So we're going to wind up multiplying by 3 here and dropping that, so that would be like r squared dr dt, and here the 3 is simplified, so I have dv dt to be equal to 4 pi r squared times dr dt, and that would be the derivative for the volume of a sphere. And the last one here, this is the Pythagorean theorem, a squared plus b squared equals c squared, essentially. So here we have to look at each individual piece and take their derivatives. So the derivative of x squared would be 2x. So I'm going to say 2x times dx dt to show that we're taking the derivative of x with respect to time there. The next piece would give me 2y times dy dt, and the derivative of the constant would be a 0. And that is the introduction to related rates, showing you how we are going to take a verbal statement and write it as a derivative math statement, and how we will take some commonly used geometric equations and write them as a derivative with respect to time, so that way we could use them to solve related rate problems based on those shapes. So thanks for watching, guys. Take care. If you have any questions, let me know. Until we meet again in class, be good, be safe, and keep being the great kids that I know you are. Talk to you later.